There's this incredible invisible balancing act happening all around us right now. It's in charge of everything from the fizz in your soda to the air we breathe and even the food we eat. It's called chemical equilibrium, and once you get it, you start to see one of the fundamental rules of the entire universe. So let's start with something we've all seen. You crack open a cold can of soda, you hear that perfect psst sound, and you see all those bubbles. But if you leave it out for a while, it just goes flat. Why does that happen? Well, that whole process, from that initial fizz to a flat drink, is the perfect story to explain chemical equilibrium. Okay, so check this out. Inside that sealed bottle, there's a ton of pressure, and it's forcing all that carbon dioxide gas to stay dissolved in the liquid. Everything is in a perfect, happy balance. It's in equilibrium. But the second you pop that top, all that pressure is released. The whole system gets thrown completely out of whack, and the equilibrium has to shift. All that dissolved CO2 makes a run for it and escapes as gas. That's your fizz. It's just the system trying to find a new, much less fizzy, balance with the air around it. That soda can really gives us the core idea. But here's the part you really gotta remember. Equilibrium isn't some static, frozen state where everything stops. No way. It's a constant, incredibly active process, a true dynamic balancing act. This is the key. Dynamic equilibrium doesn't mean the reactions are over, not even close. It just means that the forward reaction, reactants turning into products, is happening at the exact same speed as the reverse reaction, where the products are turning right back into reactants. It's like a perfectly choreographed dance where, from a distance, it looks like nobody's moving, but up close, there's constant motion. To make this crystal clear, let's paint a picture. Imagine you've got two big water cylinders. One's full, let's call that our reactants, and the other is empty, our products. At first, of course, water rushes from the full one to the empty one. That's our forward reaction. But as that product cylinder starts to fill up, water starts flowing back. That's the reverse reaction. And pretty soon, you hit a point where the water levels in both cylinders just stay put. But is the water static? Absolutely not. It's still flowing in both directions, just at perfectly equal rates. That is the heart of dynamic equilibrium. Okay, so this balance exists, but here's where it gets really, really cool. We aren't just stuck watching this happen. We can actually manipulate this balance. We can literally push a reaction in the direction we want it to go. And the rulebook for how to do this is called Le Châtelier's principle. And honestly, it's pretty straightforward. It basically says if a system is chilling in its happy equilibrium and you mess with it, you add a stress, the system is going to shift itself around to relieve that stress. It always pushes back to find a new state of balance. So, how do we actually stress a system? Let's use a hugely important reaction as our example, making ammonia from nitrogen and hydrogen. This is known as the Haber process, and the single reaction is so important for making fertilizer that it literally helps feed billions of people. Stress number 1, concentration. So according to our rule book, if we just start dumping more reactants into the pot, more nitrogen or more hydrogen, the system is going to go, whoa, we have way too many reactants. And how does it fix that? It gets busy consuming them. It speeds up the forward reaction to make more ammonia. The balance shifts to the right, towards the products. Simple as that. All right, now for pressure. Think of this like trying to stuff an overpacked suitcase. If you look at our equation, on the left side, we have 1 nitrogen and 3 hydrogens, for a grand total of 4 gas molecules. On the right side, we just have 2 ammonia molecules. So, if we crank up the pressure, we're squeezing the whole system. To relieve that stress, the system shifts to the side that takes up less space, the side with fewer gas molecules. In this case, that's the product side. High pressure pushes the reaction to make more ammonia. And finally, we've got temperature. Now, this reaction is exothermic, which is just a fancy way of saying it releases heat when it happens. So, for fun, let's just pretend heat is one of the products. Well, if we add more heat, if we add more product, what's the system going to do? It's going to try and get rid of it by shifting in reverse, back towards the reactants, which is kind of weird, right? It means that to get the most ammonia, lower temperatures are actually better. So those are the rules of the game. Now let's look at how mastering these rules has had an absolutely staggering impact on the real world. This isn't just some theory in a textbook. This is technology that shapes our civilization. Just look at that number, 100 million Tons. That's how much ammonia is made for fertilizer every single year. And that's only possible because scientists figured out how to master Le Chatelier's principle. This is, without a doubt, one of the most important inventions of the 20th century, and it's responsible for feeding a massive chunk of the world's population. So how do they pull it off? Well, it's a masterclass in pushing the balance. First, they use super high pressure to force the reaction towards the products. Second, they have to make a trade-off with temperature. Yeah, low temps give you a better yield, but the reaction would be painfully slow. So they use a compromise, a moderate temperature, along with a catalyst to speed things up. And finally, here's the really clever part. As the ammonia gets made, they constantly remove it. This keeps pulling the reaction forward, tricking the system into making more and more product. But look, this isn't just about some giant factory. This exact same principle of dynamic equilibrium is at work inside your body right this second. The hemoglobin in your blood grabs onto oxygen in your lungs, where the oxygen concentration is really high. Then it travels to your muscles, where the concentration is low, and releases it. It's a biological equilibrium that is absolutely essential for keeping us alive. Now, let's switch gears and see how this same idea works in a totally different world. Because equilibrium isn't just about gases in a factory, it's also the fundamental rule that defines what makes something an acid or a base. Believe it or not, even a plain old glass of water is just buzzing with activity. A tiny, tiny fraction of water molecules are constantly splitting apart into hydrogen ions and hydroxide ions, and then immediately snapping back together again. It's happening at a perfectly balanced, constant rate, creating this very specific and very important equilibrium. And that constant balancing act? That is the bedrock of the entire pH scale. The pH scale isn't some random system someone made up. It's a direct measurement of this specific ionic tug-of-war happening in a solution. It's really that simple. When you have more hydrogen ions than hydroxide ions, the solution is acidic, and its pH is less than 7. When they're perfectly balanced, it's neutral, right at pH 7. And when the hydroxide ions have the upper hand, it's basic, with a pH above 7. The whole thing is just a seesaw, a game of balance between these two little ions. So think about it. We've just connected a fizzy drink, the fertilizer that feeds the planet, the way you breathe, and the entire concept of acids and bases, all back to this one powerful idea of a hidden balance. It really makes you wonder, if this one invisible balancing act is so fundamental, what other equilibria are out there, quietly and powerfully shaping our world at this very moment?